This is the next video, and this video is about the equation of capacitance. So this is the next video, and this video is about the derivation of the capacitance for the capacitance due to a charge located on a sphere or a isolated sphere, and the derivation of the capacitance for a parallel plate capacitor. So we are going to use what is the derivations from the electrostatics, or the equations from electrostatics, to derive the value of the capacitance. So capacitance in general can be defined as the charge divided by the voltage. So if there is two plates which are metals and which are separated by any insulating medium, which could be example like air, mica, etc., and the charge on the plate is Q, and the voltage which is supplied across this plate is a V voltage. The capacitance of due to this plate arrangement can be known as C is equal to Q by V. And if we are we have the equation for the potential which we derived for the electrostatics, which is given by Q upon 4 pi epsilon naught epsilon r. So epsilon naught epsilon r is equal to what is known as the absolute permittivity. This is the relative permittivity, and this is the permittivity of free space. This together is known as the epsilon. So the capacitance, if you are substituting in this equation, so suppose the case which we are considering is, suppose there is a sphere which is isolated and this has a charge Q on this sphere, and there is the capacitance between the sphere and the earth or the ground. The ground is at a potential which is 0. So the capacitance between the sphere which is having a charge Q and this earth. So let's find out that. So the equation of the capacitance C is equal to Q divided by 4 pi, or Q into 4 pi epsilon naught epsilon r into r. So the capacitance due to an ideal isolated sphere can be given as 4 pi epsilon naught epsilon r into r, which is the radius of the sphere. So this is the equation of the capacitance for due to an isolated sphere, and the equation of the capacitance is given in the farad. And the next is finding the capacitance due to parallel plate capacitor. So if you are having an arrangement where these are your two parallel plates and there is a positive charge on one of the plates and there is a negative charge on the other plate, and this is the electric field is from into this side. So from the negative side to the positive side, this is what is my electric field. And if you are saying that this is D and this is my origin, this plate is located at a distance D, and if you are considering this as your reference origin, and this whole arrangement to be located on in the x-axis, and this is your AX unit vector, and you can also consider this plate to be connected to a ground, that is a negative, and the area of this plate is S. So the surface charge density can be written as Q by S, and the charge on each of the plate, if you are assuming it's Q, and you can say that the electric field intensity is in the direction of the field, or direction in this direction, which is, this is a negative x direction or this is a positive x direction. The electric field intensity is minus rho s into ax. This is a electric field or electric field density. This is the electric field density equation. So it is known that the electric field density can also be given by epsilon into E, where epsilon is the permittivity of the medium, and you can write it as D is equal to epsilon S into AX, which is in the minus direction, into the epsilon. So this is equal to your E, which can be given by, so this whole thing which is here is equal to my epsilon E from this equation. So this is my first equation. If I take this is the second equation, and based on the first and two, you can write it is equal to rho s into minus AX. So my electric field intensity will be rho s divided by epsilon into minus AX, which is a vector direction, and my rho s will be is equal to Q by S. So my electric field intensity E will be equal to minus Q upon epsilon S and the direction of the vector. So if I'm finding the potential then it can be given by the equation which we have derived, and this is a first plate and this is a second plate, and if I'm moving from second to 1 in the direction of the electric field, then it can be given in the E dot dl, so which is a derivation which is moving from 0 to d and minus in the negative direction or in the direction against the field, so it will be in the negative. And if I am giving this same thing which I am substituting here, then it will be epsilon s into the dl will be ax here. So this is ax here and ax into ax vector. So my V is equal to Q upon epsilon s into d. This is the equation which I am getting after solving this. So if I say that this is my third equation, then I can say that my C is equal to Q divided by V is equal to epsilon s divided by d, where my S is equal to my area of the plate. So this is what is my equation of a parallel plate capacitor, and the energy stored in the capacitor is given as half CV square, which is equal to half QV. So this was how I derived the equation of a parallel plate capacitor.